Okay, we're building our mathematical models today. Today we're going to learn about this thing called the multiplication rule. Now, I think this is the third or fourth time I've talked about what independence means. Okay, I think there's 3 or 4 more times I'm going to bring it up. It's that important. Okay, that you understand what it means for 2 events to be independent. I don't care, I just kind of wrote this 2 different ways. But 2 events are independent if some other event happens and it has absolutely no effect on the next event happening. Flip a coin. So I flip a coin and hey, I know I got a heads just before that. Does that affect the next flip at all? Is it going to change the probability of being heads from 0.5 at all? No. So when I ask you a question, are these 2 events independent, you always want to ask yourself that question. Does the first event happening in any way, shape, or form affect the second event? If I deal you cards and you pick a card, okay, then I'll take that card back, I put it back in the deck, I reshuffle, and I have you pick another card. Can we say those 2 events are independent? I'd say yeah. So let's say you got a heart. I put it back in here. Then I have you re-pick from the 52. Is the probability of getting a heart going to be any different than it was before, even if you got a heart before? No. But now, if I give you that card and the card doesn't come back in the deck, does the fact that he got a heart, would that change the probability that the next one would be a heart? Yes. And in that case, we say they are dependent. Okay? I really need for you guys to not confuse mutually exclusive, which we learned about yesterday, and independence. Mutually exclusive means that the 2 events cannot happen at the same time. Okay, if one event happens, the other one can't happen. Okay, mutually exclusive, they cannot happen at the same time. Yesterday I gave you an example of something that wasn't mutually exclusive. You know, if I want to know the percentage of people that love football, and another event, the percentage of people who love hot dogs. Are there probably some people that love both? Sure. Okay, so those events are not mutually exclusive. Are the events that I am a boy and a girl? I don't want any debate about that. Are those going to happen at the same time? The answer is no. So we'll say those events are mutually exclusive. Okay, I need you to keep these 2 separate. They mean totally different things. Remember, you had to make sure that the events were mutually exclusive in order for you to use that addition rule yesterday. They couldn't happen at the same time. Today, the events have to be independent. That's the only way you're going to be able to use this multiplication rule. However, there is a relationship between the 2. I need you to keep the concepts separate, but there is a relationship, and I'll get it started for you. This is the only kind of way it works. If 2 events are mutually exclusive, then think about that and fill in the blank. If 2 events, if you know 2 events are mutually exclusive, then those 2 events must be, so you got 2 options here, independent or dependent. That's what I'm looking for. Really think about this for a second. You got a guess from? If 2 events are mutually exclusive, then those 2 events must be
independent.
Independent? Why?
Because they both happen on their own. Both.
There's no definitions there. What do you got?
They both don't have...
Well, what are you going, independent or dependent?
Independent.
Independent, why?
Because their outcomes don't have anything in common.
But does that have anything to do with them having any relationship to each other? If I have 2 independent events, look, loving football and loving hot dogs, those seem kind of independent, don't they? But they can still happen at the same time. I don't know if I just gave the answer. Yeah.
Dependent.
So you think if 2 events are mutually exclusive, they must be dependent. Why?
Because if they're mutually exclusive, then one outcome means it can't be the other outcome, so there's a relationship of...
Does everybody get what he just said? I had a great example last period. The person said, okay, let's say you're going to pick a couple cards, okay, and you get the 2 of clubs, okay, and let's say we don't replace it. do I now know the probability of getting the 2 of clubs again? What is it? 0. It can't happen. So therefore, there's a dependence, right? If I know the first event happened, then the second event cannot happen. So knowing that event happened before affects the probability of the next event happening. So if you know 2 events are mutually exclusive, it does follow that they are dependent. But please, when I say the word mutually exclusive or I say the word independent, you have to know what those 2 things mean separately, because you're going to get them confused. You're going to use them in different situations. All right, so if we know that 2 events, yeah.
Well, in your football hot dog example.
Okay, I just threw that one out there. I hope I didn't mess it up. Okay, so I got a football and hot dog, 2 different events. Okay.
How would they depend on each other?
I don't think they do.
Well,
They may, but I don't think they do. I think knowing, well, I don't know, let's ask this. If I know someone loves hot dogs, well, I don't know now, maybe let's think about this now. If you know you've got someone that loves hot dogs, do you think that's going to change the probability that they love football?
Need to do a simulation.
But I don't know if there's a right or wrong to this. Let's think about this. If you know someone, I got this person over, they love hot dogs. Do you think that rises or lowers the probability that they also love football?
What's the population?
Everybody. Everybody in the world. Everybody in the United States, let's say.
Rises.
probably not.
I think, well, I mean, I don't know, do more guys like hot dogs than girls, or is it even on that? I don't know, but you see what I'm saying? There's some debate here. I don't know if they're independent or not. I really don't. You have to go through that process of saying, okay, I know someone here likes hot dogs. Does that change the fact that the person will like football? Okay, so you got to go through that. We're actually going to be doing more work with this real soon. All right, if you know 2 events are independent, then we can find out the probability of both events happening by simply multiplying them together. All right, let me show you how this works. So let's say we've done this flipping a coin thing twice, quite a bit, right? What are the different options? So there's heads, 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 tails, tails, heads, and tails, tails. So there are 4 different elements of the sample space. Okay? If I was trying to figure out what's the probability of getting heads and a heads, getting heads on both, isn't that going to be 1 over 4 or 25% by our rule of probability? Well, let me just show you another way we can get that. Okay? Are flipping coins independent? You've always got to ask yourself that question first. Is flipping coins independent? Yes, they are. So what we're trying to figure out here is what's the probability of getting a heads on the first and a heads on the second. Since they're independent, we know that's the probability of getting heads on the first times the probability of getting heads on the second, which we now know is 0.5 times 0.5, and we get the same exact answer. Obviously, this guy's going to be a lot more convenient, just flipping a coin 100 times rather than trying to figure out all those out for 100 of them. Right? Okay, so 2 different ways to get the same answer. All right, let's try another one. All right, let's go with that drawing 3 cards thing. Okay, so now we're going to draw 3 cards out of a deck, and I'm going to replace it. So after I give you a card, I'm going to put it back in the deck. So are we talking about an independent situation?
Yeah.
Okay, good. All right, so I want to know the probability that I'm going to draw 3 hearts in a row. Okay, since I have an independent, and I want to know the probability of getting a heart, and a heart, and a heart. Okay, this is how I would write it up. I want to know the probability of the first card's a heart, the second card's a heart, the third card's a heart. Because they're independent events, I can multiply the 3 of them together. The probability of getting a heart, right, is 1/4. There's 52 cards in a deck, 13 of them are hearts, so that's 1/4. That's where I got the 0.25. So 0.25, 0.25. So in the long run, there's about a 1.5% chance if I deal you 3 cards with replacement, okay, that you're going to get dealt 3 hearts. Okay. I want you to look at last night's homeworks. Nobody asked about it. I'm kind of confused. Let's take a look at the very last D and E. Let's just do D, for example. So I'm looking at 26D. The correct answer was 0.426. My question to you is, is, can I use the multiplication rule? Some of you may have. I looked at some of your homeworks last night. You just multiplied two things together. Can I use the multiplication rule for this problem? What?
No.
Why not?
Because this is dependent.
What? Great. Now to figure out if they're dependent, now here's the deal here. So let's look at the two events. The two events are you get an odd digit, okay, and the digit has to be less than 4. So how do I prove independence? I say, okay, let's assume I got an odd digit. So what are the odd digits? 1, 3, 5, 7, and 9. So let's assume that I got an odd digit. Does that now change the probability that I got one that was less than 4? What's the probability of getting a number less than 4? Look at the problem. The probability of getting a number that's less than 4 is 3 over 9. Right? The probability of me getting a number that's less than 4 is 3 over 9 to start the problem. Now, let's say that the first thing happened. So the digit is odd. Is that the first thing? Yeah. Does that now change the probability that it was less than 4? Well, if I got an odd digit, there's only 5 of those, 2 of them are less than 4, that's 2 over 5. It did change the probability. Did you follow that?
Oh yeah, no.
Okay. So you're correct. They're dependent. So if you just see that symbol, don't just go right into multiplication mode. You have to make sure that the events were independent before you can use this. Okay. All right. So let's go through this. Often, I've never shown this early in the chapter yet, but it comes up so much and it's so important. Quite often, this multiplication rule can really be simplified, or you can look at it better by drawing the tree. So what I've got here is a tree of drawing 3 cards with replacement. Okay, does everybody kind of follow this? The first card could have been a heart, then not a heart, would be 75%, right? 75% chance of not getting a heart, and then a heart on the last one. Okay. So how the multiplication works with a tree is you just multiply your way down the tree. Probably getting the first heart is 25%, 25% for the second heart. Now I'm not going to draw this, but next period. But you could just draw that through, and so this becomes 20.25 times 0.25 times 0.25, and we end up getting our 1.56%. All right, now we get into the tricky stuff. Why is probability so hard, at least for me? Well, I think each one of these rules on their own is kind of like, okay, I get that, I kind of get that. That makes sense. But it's when I ask you for problems that combine the rules, where you're using 2 or more rules on the same problem, like we're going to do in the birthday problem pretty soon. So let me give you a couple of examples of things you're going to see. You're going to see these, I think, all on your next test, in May 10th. All right, what if... This is my probability model for the number of hearts I have in my 3 cards. Is everybody okay with what I got so far? I got 3 cards. I want to count how many hearts I have. Are these all the possibilities that there are? I might have no hearts. I might have 1 heart. I might have 2 hearts. I might have 3 hearts. Is everybody okay with that? Now, what if I ask you the question? I want you to tell me the probability that I will have at least 1 heart in my hand. So at least is kind of a couple of key words that I want you to be on the lookout for, because it should. What does it mean? What does it mean if I'm asking you for the probability that at least one of those cards is a heart? What am I actually saying? Okay, so in my hand I might have 1 heart, or 2 hearts, or 3 hearts. So are you okay with what she just said? Isn't that what at least 1 heart means? So could I say this? That's really these 3 guys added up? Isn't that the probability of getting 1 heart, or 2 hearts, or 3 hearts? Okay, now, you're going to find out in a second, finding these are pretty difficult. But, is there an easier way to figure out what those 3 must add up to in this problem? What would be kind of a good way to do it?
PS equals...
No, don't give me any formulas. What? Just in my picture here. What would be, if I want to figure out what these 3 are added up, I could... That's what we're going to use, yeah.
Find the 0.
Yeah, how about find that guy? Can we first find out the probability that I got no hearts? And then what would you do? Subtract it from 1. So it's kind of like this. You'd be like 1 minus this equals this. Right? Every year people laugh at me when I do that. I think that's brilliant. All right, go find that. Go find the probability that you're dealt 3 cards and none of them are hearts. Go. So I want the probability that I don't get any hearts. I don't get a heart. I don't get a heart. And I don't get a heart. Not in your calculator, on your paper. How would you do that? Show me the steps. If you're using a formula, show me that formula. Okay, we still have independent events, right? So what I'm looking for here is the probability that I don't get a heart on the first one, and I don't get a heart on the second one, and I don't get a heart on the third one. Since these are independent events, it's the probability of not getting a heart on the first, times not getting a heart on the second, times not getting a heart on the third. And what is the probability of not getting a heart? 0.75, is that right? 0.75, 0.7, so is that 0.75 to the third? So this is approximately, that's roughly 42%. Right?
Yeah.
So what is the probability of at least? 1 minus the 42%, which is 58%. So take a step back. What did we do here? Okay, we had a problem that just asked us nice and, innocent-like to find out at least 1. So we used the multiplication rule, right? Then we multiply our way down this tree by using the multiplication rule. And then we used our knowledge that they have to add up to 1 and use the complement rule to figure that out. All right, now, next one, which is this is a really sneaky one. What if I asked you to find just that guy? I just want to know, we're playing this game, what's the probability that I'm going to get dealt 2 hearts? That's all I want to know. What's the probability that I get dealt 3 cards, that 2 of them will be hearts? First thing that comes to your head, help me out, somebody. Yeah.
Find the probability of getting no hearts and 1 heart.
Okay, so good. So I said 2 hearts and 1 not heart. Okay, so what 2 hearts is, and I would write a formula, but I'm just going to net it out here. So not heart was what, 0.25,
Yeah.
and then 0.25, and then 0.75. That would be the not heart, and I'm done, right? No, I said it that way. That's why you're shaking your head no. Why no?
Because you have both sides of the tree.
Yes. Now let's think about this for a second. Isn't there more ways than just one way down this tree to have 2 hearts and 1 not heart? Isn't there this way? This is the way you just described to me. I get heart, heart, and then not heart. So that's 0.25, 0.25, 0.75. But are there other ways that can happen? In fact, there are 2 other ways I think it can happen. I could go heart, not heart, heart. And there's another one down here too. Not hearts, heart, and heart. Now here's the question. So I've used the multiplication rule to find each one of those. Now, aren't these events mutually exclusive? Mutually exclusive. Okay. I can't get dealt 2 hearts, then a not heart, and then 1 heart, not heart. That can't happen at the same time, right? That can't happen at the same time. So if it can happen this way, or this way, or this way, what would I do with those when I got them together? I would add. That's the addition rule. So we're using both the multiplication rule and the addition rule on the same problem.
So in a problem like this, can you just get one of them and then multiply by the number of
Yes,
paths.
and you or I would maybe just add the 3 or multiply them by 3. That's a good shortcut. We'll talk more about that later. But for right now, I'd write the formulas and I'd show that I'm adding them.
To show the whole tree.
Well, you got a couple of options here. You could try to do this all with formulas, or if it's not too big, you could show it on a tree real nice too. I'll take either one. Now, if I'm drawing 10 cards, you ain't gonna be able to use this, right? So you're gonna have to somehow do it with formulas. Okay? All right. Big deal. Got to be independent. Don't use this formula unless you know these two events are independent. But if they are, we don't got to do this. We've got a nice little shortcut that'll tell us the probability of a certain event happening. Okay? Any questions?